All right, welcome and thanks for joining for the examples video. So we'll try and keep this a little bit quick, but some of the later slides have a little bit more work. So evaluating exponential functions, finding the value of f at x. If I have f of x equals 3 to the x, and I want x to be equal to -2, then when I find f of -2, I get 3 to the -2 power. When we have negative exponents, this is something that people really struggle with a lot of the time. A negative exponent means that this can be rewritten as 1 over 3 to the positive second power. Now, fix that a little bit. So the negative in the exponent just pushes this to the denominator. And then 3 squared is 9, so this is 1/9. If I have 2/3 to the -3, so I'm going to have f of -3 is equal to 2/3 to the -3rd. So first, I'll deal with this negative exponent. And what that does to a fraction is it just flips it over. So this becomes 3 over 2 to the 3rd. And now, when I have a fraction raised to a power, I can just raise the numerator and denominator separately to that power. So 3 cubed is 27. 2 cubed is 8. Next, 0.5. So f of 0.5 is equal to 5 times 2 to the -3 times 0.5. And I'm just going to give myself a little bit more. There we go. I think this one will be a little bit longer. So -3 times 0.5 is going to give me 5 times 2 to the -1.5. When I talk about being raised to the -1.5 power, that's the same as having 5 times 2 to the -3/2 power. I just rewrote that fraction. So this is going to give me 5 times 1 over, because this negative pushes me into the denominator, 2 to the 3/2 means I'm doing 2 cubed, but this denominator of an exponent is going to tell me what type of root I'm taking. So I'm taking the second root, or the square root, of 2 cubed. This gives me 5 over, I did 5 times 1. 2 cubed is 8, so this becomes square root 8, which is 5 over, if I simplify this, 2 root 2. And remember that we have to rationalize these. So this is 5 root 2 over 4. There's a lot of wonderful skills that go in there, rewriting this decimal as a fraction, knowing how the fraction is going to look as a radical, simplifying a radical, rationalizing, but don't think of that as being what's going to be standard in most problems. All right, next, if I want f of -1, it's going to be -4 times 1/3 to the -1 minus 2. That gives me -4 times 1/3 to the -3. 1/3 to the negative, that means that this is going to flip over and become 3, and it will be raised to the positive. Three cubed is 27, and 27 times -4 is -108. So there, all that's going to help us for is a lot of the cases where what we're looking to do is find some points on an exponential function. All right, moving along. Graph each function and identify the intercepts, asymptotes, and tell whether it's increasing or decreasing. So I'm going to start really quickly just by giving us little sketches for each one of these. Right, sorry about that. So now, if I'm going to be labeling the intercepts, asymptotes, and tell whether it's increasing or decreasing. So looking at this is a basic function. It's a to the power of x. which means that there's a horizontal asymptote of y equals 0. So I will start with that. There's my horizontal asymptote, y equals 0. One of the coordinates on this graph is always 0, comma. If I put 0 into this, I would have 3 halves to the 0 power, which is 1. So 0, 1. If I put 1 into this, I'd have 1 to the power of, or I'm sorry, a, which is 3 halves to the power of 1, which just gives me 3 halves. So 1 comma 3 halves is 1.5. So we have our intercept, we have our asymptote. If we draw this function, then we know it must be going like this, which means that this is increasing. Going from left to right, it would always be rising. Next, we have 3 halves to the power of x plus 2. So this is sort of an interesting question because you can do it in one of two ways. You could graph the original function as if this plus 2 is not here. Imagine that's not there. And then shift the function over 2 units. Or just using coordinates, you can come up with it regardless. So first, let's talk about that horizontal asymptote. If we're talking about a horizontal asymptote, you're thinking about some horizontal line that's usually at 0. This shift represents something that's to the left 2 units because it's in the exponent. So if I were taking this line and shifting it to the left 2 units, it's that same line. So my horizontal asymptote hasn't changed. It's still y equals 0. In terms of my coordinates, you can still think about substituting in 0 and 1, even though this isn't a basic function. If I were to substitute 0, I'd get 3 halves squared. So I'd have 3 squared, which is 9, and 2 squared, which is 4. So 0, comma 9/4, which is a little bit above 2. Then talk about substituting 1 in. If I substitute 1 in, the exponent would be 3. So 3 cubed is 27. 2 cubed is 8. And 27/8 is a little bit above 3. So I'd have this exponential function. Notice we couldn't just use 0, 1, 1a because this wasn't a basic function. It's been shifted. All right, moving forward. We have 3 halves to the x plus 2. So first, talking about that horizontal asymptote, it's usually at 0. This shift represents going up 2. So if it was usually at 0 and has now been shifted up 2 units, it's now at 2. So y equals 2. Sorry, just to go back really quick, this is also an increasing function. From left to right, it's always rising. Okay, going back here. So 3 halves to the power of x plus 2. Now I'm going to take these two coordinates, 0 and 1. If I substitute 0 into this, I'd have 3 halves to the 0, which is 1, but plus 2. So that becomes 3. If I substituted 1 in, I'd have just 3 halves, but plus 2, 3 halves plus 2. If I wanted to write 2 as something over 2, it becomes 4 over 2. So this is 7 halves, which is 3.5. And my exponential function would look like this. Also increasing. Last, we have 3 halves to the negative x. So this negative x, I'm changing my x value, which means I'm reflecting over the y-axis. So if we think about a reflection over the y-axis, it's not going to change our horizontal asymptote. And we can still, if we wanted to, substitute in points to this. If I were to substitute in 0, I'd have 3 halves to the 0, which is 1 still. If I substitute in 1, I'd have 3 halves to the negative first. The negative flips this over, so it becomes 2/3 to the first power, which is just 2/3. Well, 2/3 is below 1, so now it's down here. And what you'll see about this function is now it goes the other direction. This is a decreasing function. Again, you could do that also just by graphing the original function and then doing the shift. I prefer to just use the coordinates, and it's what I do, I think, for logarithmic functions as well when we get to those. All right, moving along. So doing some of this growth decay scenarios. What would the balance be in an account if you were to deposit $5,000 for 5 years at 6% interest rate, compounded, and then I'm going to give a couple different number of times. So first, the initial amount that you're putting in, the principal, is $5,000. The time you're putting it in for is 5 years. The rate needs to be as a decimal, so it's going to be 0.06. What we're talking about here is different types of compounding. So if I'm compounding once in a year, that's going to be n being 1. If I'm going to compound monthly, there's 12 months in a year. And if I'm compounding weekly, there are 52 weeks in the year. So we would just do A equals P, which is 5,000, times 1 plus, and then we have R over N, sorry. So we're going to have 0.06 over N, which is 1, raised to the power of N times T. So N being 1 times T being 5. All you would do is shoot that into your calculator. I don't expect you to, be able to do that all by hand. But what you get in this case, rounded to 2 decimal places since it's money, is $6,691.13. Monthly, we have A equals 5,000 times 1 plus 0.06. The only thing that has changed here is N. So when we have R over N, this will now be 12, raised to the N times T, so 12 times 5. That's going to give me $6,744.25. So we got a little bit more money. If we were to compound weekly, we'd have A equals 5,000 times 1 plus 0.06 over 52 to the power of 52 times 5, which now gives me $6,748.13. So not, a huge jump going from monthly to weekly. We saw a big jump going from once to monthly, though. So let's talk about a little bit more growth decay type stuff. What would the balance be in an account if you deposited $12,000? So I'm depositing $12,000 for 18 months. Now, 18 months, I need to think of this in terms of years. 18 months is 1.5 years. And at a rate of 0.08 or 8%. Compounded daily means N is going to be 365. Hourly means N is going to be equal to, there are 365 days in a year, 24 hours in a day. So hourly is going to give us, 365 times 200 or 24, whatever that gives us. And continuously means we're going to be using a different formula, so we're not going to have to worry about N. So if I want daily, A equals P 12,000 times 1 plus R 0.08 over N 365 raised to the N 365 times T 1.5. And what that gives me is 13,528 0.78. And again, that's just a matter of typing this into your calculator. Hourly, we'd have A is equal to 12,000 times 1 plus 0.08 over whatever I get when I do 365 times 24, raised to the power of 365 times 24 times 1.5. That would give me 13,529 and 95 cents. So you could sort of see here, when I went from compounding once to monthly, there was a relatively big jump, like $50 over the year. When I then said, well, what if we compounded weekly instead of monthly? That was only $4 per year. When I talk about even more money initially, $12,000, and daily versus hourly, I barely see a gain. It's a little bit more than $1 over the entire year. If I talk about continuously, so that's the formula A equals PE to the R times T. So we would have 12,000 times E. Remember that E is not a variable, it's a number, so we're not substituting anything in there. To the 0.08 times 1.5. What this would give me is 13,529 and 96 cents. So going from hourly to continuously over the entire year, that only gets me an extra cent. So why do we talk about continuous growth or decay? You know, it's in money, okay, cool, I got a penny. But it does naturally occur in some other things, like in this case, if we're talking about decay of carbon. So let Q represent a mass of carbon-14 in grams, whose half-life is 5,730 years. The quantity present after T years is given by the formula Q equals 10 times 1/2 to the power of T over 5,730. This is the initial amount times, this is half-life, so half, to the power of time over what the half-life is, 5,730. So this is the actual half-life of it. What amount of carbon is present at T equals 0 years? So you could think about this conceptually, or you can actually substitute it in. If I substituted 0 into this, I'd get 1/2 to the 0 power. 1/2 to the 0 power gives me 1, and 1 times 10 is 10. So 10 grams. You can also say at 0 years, I have not yet started to decay. So when I said that I had 10 grams here, that's how much I'm going to be starting with. What quantity is present at T equals 1,500 years? So all we would do is go to Q is equal to 10 times 1/2 to the 1,500 over 5,730. And what that's going to give me is Q being approximately 8.34 grams. So after 1,500 years, those 10 grams of carbon would now just be 8.34 grams of carbon. Estimate the time needed for 4 grams of the initial quantity to remain. So this would be something that we would use our calculator for. I mean, obviously this is something that we used our calculator for, but it's using it in a different way that I might want to show you in class. So, you know, just a little friendly reminder. But what we want to know is, when are 4 grams going to remain? Well, Q represents the amount of grams remaining. So we'll have 4 is equal to 10 times 1/2 T over 5,730. And I'll tell you that this is T being approximately 7,000 years. But what I do is I get that from a graph where I looked for when these two functions would be equal to each other. We will get to how we algebraically solve that, but that's later on in the chapter, because we have to figure out how we're going to get rid of this 1/2. You know, if we were thinking about this, this is 4 equals 10. So 1/2 T over 5,730. So we divide by 4, we get 2/5 equals 1/2 to the t over 5,730. You can't divide by 1/2 in this case, because what we always say is it's the operation that's in between these two things that you have to get rid of. Well, I'm not doing 1/2 times this. I'm doing 1/2 to the power of this. And that's where we're like, I don't know. I haven't dealt with that before. So I don't know how to get rid of this 1/2. And that's what we'll deal with later on in the chapter. But for right now, we could still do that question using a graphing calculator. All right, make sure that you understand everything that's on here. If you want to get started on 3.1 homework, feel free to do so.